Hello everyone, I'm your instructor, Wang Shengda. In this lesson, we will study the factors influencing chain flexibility. Through this lesson, you will know the factors that affect the flexibility of polymer chains. Learn to evaluate the flexibility of different polymer chains. Develop the ability to summarize and generalize key concepts. Different polymers exhibit different degrees of chain flexibility. The main factors influencing polymer chain flexibility include the structure of the polymer backbone, the structure of side groups attached to the main chain, branched structure, cross-linked structure, and the intermolecular forces. Backbones that consist entirely of single bonds generally exhibit good flexibility, such as polyethylene and polypropylene. Since different single bonds have different bond lengths and bond angles, and longer bond lengths or larger bond angles allow easier internal rotation. The flexibility varies among single bonds. The general order of increasing flexibility is SiO bond, more flexible than Cn bond, which is more flexible than CO bond, which in turn is more flexible than Cc bond. Double bonds consist of a sigma bond and a pi bond. A double bond cannot undergo internal rotation. This is because rotation of the pi bond would disrupt the electron cloud distribution, effectively breaking the chemical bond. This means a chemical reaction would occur. Therefore, a double bond cannot rotate. So, a polymer backbone contains many double bonds, especially conjugated double bonds where single and double bonds alternate. The polymer chain exhibits poor flexibility, such as polyacetylene and polyphenylene. In other words, such polymers have highly rigid chains. However, when the backbone contains isolated double bonds, where single and double bonds do not alternate, the polymer chain tends to be more flexible. Although the isolated double bond itself cannot rotate, the two carbon atoms at its ends have fewer non-bonded atoms, make an internal rotation on both sides of the double bond easier. For instance, polybutadiene is even more flexible than polyethylene, which contains no double bonds at all. When aromatic rings or heteroaromatic rings are present in the backbone, the chain flexibility decreases significantly. The reason is the same as that for polymers whose backbones contain conjugated double bonds and therefore have poor flexibility. Aromatic rings or heteroaromatic rings also cannot undergo internal rotation. Polymers such as polyphenylene oxide and polycarbonate exhibit poor chain flexibility. Next, let's study the effect of substituents on chain flexibility. The stronger the polarity of a substituent, the greater the intermolecular forces, make an internal rotation more difficult and reducing chain flexibility. For example, in polyethylene, polyvinyl chloride, and polyacrylonitrile, the substituents, hydrogen, chlorine, and cyano groups have increasing polarity, and the chain flexibility decreases accordingly. The larger the volume of a nonpolar substituent, the greater the hindrance to internal rotation, and the lower the chain flexibility. For example, in polyethylene, polypropylene, and polystyrene, the substituents, hydrogen, methyl, and phenyl groups gradually increase in size, resulting in decreasing chain flexibility. For cases with symmetrically substituted side groups, where two identical substituents are attached to the same backbone carbon, the polymer chain exhibits better flexibility. For example, in polyisobutylene, two methyl groups are attached to the same backbone carbon, giving it higher chain flexibility than polypropylene. Similarly, in polyvinylidene chloride, two chlorine atoms are attached to the same backbone carbon, resulting in greater flexibility than polyvinyl chloride. On the other hand, the higher the proportion of substituents, That is, the shorter the spacing along the chain or the greater the number of substituents, the lower the chain flexibility. For example, polychloroprene contains fewer chlorine atoms than polyvinyl chloride, so its chain is more flexible. Next, we will study the effects of branched and cross-linked structures on the flexibility of polymer chains. The impact of branched on chain flexibility depends mainly on the length of the branches. Short branches increase the distance between polymer chains and reduce intermolecular forces, thereby enhancing chain flexibility. In contrast, long branches tend to reduce chain flexibility. For example, among low-density polyethylene (LDPE), linear low-density polyethylene (LLDPE), and high-density polyethylene (HDPE), the degree of branching decreases in this order. LDPE has the highest, followed by LLDPE, and HDPE has the lowest. Accordingly, their chain flexibility follows the same order. LDPE is the most flexible, LLDPE comes next, and HDPE is the least flexible. The effect of cross-linked on chain flexibility is closely related to the degree of cross-linked. When the cross-linking density is low, the impact on flexibility is minimal. However, when the cross-linked density becomes high, the single bonds between cross-linked points can no longer rotate freely, and the polymer chain loses flexibility. In addition, the greater the intermolecular forces, the lower the flexibility of the chain. In general, polymer chains that contain polar groups are generally less flexible than those without them. That is, than nonpolar polymer chains. And if the polymer contains hydrogen bonds, its flexibility becomes even poorer. For instance, DNA, which contains numerous hydrogen bonds, is a typical rigid macromolecule. In this lesson, we mainly discussed how the backbone structure, substituents, branched, and cross-linked influence the flexibility of polymer chains.